In this video, we're going to talk about causality and how you can describe it mathematically and how you can use graphs to visualize it. First of all, why do we even worry about causality? Well, models that explicitly encode causal relationships are the only useful models. The good thing is that physical and engineering models are often causal models. You just need to learn how to interpret them as such. And the problem is that when you extend the physical or engineering models to account for uncertainty, you need to make sure that these extensions remain causal. Otherwise, if you don't pay attention to that and you blindly build models and you calibrate them on data, you may end up with models that capture just correlations between variables. And these models that capture just correlations, are completely useless because you cannot use them to make decisions. You cannot trust these models. The reason is that models that just capture correlations cannot tell you what's going to happen to one variable if you intervene and you change the value of another variable. Causal models tell you that. Now, structural causal models is a mathematical way of describing causality. It's a way to formalize causal mechanisms mathematically. And let's see what it is all about using an example. Now we're going to use an example from a medical field. And the first thing that we're going to do is we're going to describe all the variables that play a role in this particular situation. And the situation here is going to be what is the effect of a treatment on asthma. So let's gather all the players first. We're going to define a variable y, indicating whether an individual has asthma or not. So this variable could be a binary variable taking two values, 0 and 1. 0 could correspond to the individual does not have asthma, and 1 could correspond to the individual has asthma. Another variable that we would like to have in our game is x, which is whether or not a patient is being treated. And again, this is a binary variable and it could take two values, 0 meaning the patient is not treated, or 1 meaning the patient is treated. That's pretty much it for the treatment and the disease variable. But maybe there are other things that affect whether or not an individual has asthma. Maybe there are other factors that cause asthma and or affect whether or not the treatment is working. And an example of that is the air pollution level, and which we indicate here by z. This variable can take, let's say, 3 different values. There's no air pollution, there's a little bit of air pollution, there's a lot of air pollution. 3 different values, 0, 1, 2. Now, that's the first step, coming up with all the players in this game, coming up with all the variables that have some role in this situation. The next thing that we need to do is to come up with functions that describe how these variables are connected. And here, for example, we may need the function f that tells us how x and z, how the treatment and the air pollution level conspire to give a value to y, which is whether or not the patient has asthma. Now, these functions here are to be interpreted as causal mechanisms. So f is describing how x and z cause y. That's how you should interpret these functions. Now, the collection of all these variables along with these functions is called a structural causal model. Now, to each structural causal model, there corresponds a directed acyclic graph. That is a graph that has edges that are arrows, and it is acyclic in the sense that the arrows do not form a cycle inside a cycle in the graph. Now, the edges here in this graph represent a direct causal link between the parent and the child node. So here, the treatment X is directly affecting whether or not a patient has asthma, why. And the same thing happens between Z and Y. Z directly causes Y. But there's no connection between X and Z, and the absence of an edge means that we believe as researchers that there's no connection between X and Z. X does not cause Z and Z does not cause X. The two things are independent. So to each structural causal model, there corresponds a directed acyclic graph. Now in practice, the way we build models is the other way around. We first draw a graph that captures the connections or what we think about the causal links between all the variables that we have, and then we try to turn all these connections into functions that describe the causal links. It goes the other way around.